Okay, my experiment is about two things. First, are there any other driving forces other than the heart is driving the blood circulation? And second, how does it work? This is my PhD project, and I've been working on this for 7 years. 7 years.
Did you expect it to take that long?
No, no. I was expecting maybe I could have graduated in 4 or 5 years. The average amount of time for a PhD program in our department is like 5.5 years. I'm definitely dragging down the whole department. Yeah, I'm still very excited about what I do, and I would say that I'm just as excited as a first year. Yeah, the first time I heard of this project, I was having lunch with my advisor, Dr. Pollack, in the cafeteria. I was like, are you kidding me? Yeah, so that was actually my first reaction. But later, after I did some literature research, and I decided to take this project because it seems promising, and it really looks like there is some missing links in the current circulation model. So yeah, I took the task. My project is about the mechanism of blood circulation. The idea is that heart is not providing all the driving force that is needed for blood circulation. Instead, light, especially infrared radiation, can be part of the energy source. This idea was first introduced in the manuscript in Jarrett's book in the year, that was like 6 years ago. So when I was reading the manuscript, I didn't expect that I'm gonna do that for as a PhD project. Later, after I got into graduate school and I was assigned with this project, the idea is that our lab, we found a phenomenon that if you put a piece of tube made of hydrophilic materials in water, and you put some microspheres in the water as flow indicator, without any external pressure gradient, you can see some flows within the tube, just as if there's an invisible pump is pumping the fluid. So what is the driving force? Light can drive the spontaneous flow in the tube. So if you shine more light on the flow will go faster. If you shine a specific wavelength of light, the flow will behave differently. So later we found that light is a determining factor for the flow. So the first thing that we start to do is that to experiment whether this flow is an exclusive feature of a certain material or is a general feature existing widely in the nature. So this flow was first spotted in tubes made of naphthalene. Naphthalene is a hydrophilic polymer. It has a backbone of Teflon and with some acid functional groups. So that's the first material. Later, I tried different material. I tried, first we observed everything in naphthalene, and in the previous work, people had already observed it in other polymer materials like PAA and PVA and PEG gels. So later I started to, when I got this project, the first thing that I started to do is to try other different materials from the nature. I tried some gels that is from plants like agar or alginate, and later I tried some gels from animals like gelatin and collagen. I observed flow in all those materials. Then we started to wonder, so everything shares one thing in common, is water. They are all hydrogels. That's gels that contains water. And our blood vessel, the body, our body is actually not so much different from hydrogel. It contains water, and our body, 2/3 of the weight of our body is water. It can be, treated as a big chunk of gel. If this flow can exist in tunnels made of regular hydrogels, so it is possible that the flow may exist in the vascular system. So that's where everything started. So after I found the flow in hydrogels, I was assigned with this project that light may drive the blood flow in the heart. The first time I heard of this project it's it's astonishing because everybody knows that heart drives the blood flow. So frankly speaking, I was shocked the first time I know this. I heard this idea that something else may drive the blood flow, and so a logic thinking is that if such a driving force really exists, the heart, the blood should still flow after the heart stopped pumping. So that's when I started to look for references that for documentation, documents that the post-mortem blood circulation, the blood flow after heart stops. So that's how I found the reference of the Israeli group. Yeah, so I started to actually that group, they are mostly working on, I think they are working on imaging. They are mostly working on vascular imaging. So they use OCT and other ways to detect the blood flow. So in that paper, originally they were trying to seek for a biological 0 point for blood flow. A biological 0 point, which means what's the signal look like if there's no blood flow at all. So that's why they euthanized the mice first and then measured the blood flow, but they couldn't totally cease the flow after the heart stopped beating. So the biological point is actually, very interestingly, it's not a stopped flow. It's just a very, very slow but continuous post-mortem blood circulation. Usually what we think is that when the heart stops beating, the blood cells in the blood should exhibit Brownian motion, so they're jittering around doing the random movement. They shouldn't flow in a certain direction. That's out of expectation, but it's been observed. I want to test the hypothesis that light is driving the blood circulation. So I use chicken embryo as a model, but I use dead chicken embryo as a model. I observed the blood circulation after I euthanized the embryos, because the heart of the embryo is beating all the time, and light apparently has some effect on the beating rate of the heart. That's a factor that we don't want to take. We want to prove the point that light is directly driving the blood flow, not by any other factors. So this is how it works. This is how light usually regulates the blood circulation, like in our body. Part of us, it can be our skin and can be our eyes, will receive the light. There are some photon receptors on our skin or in our eyes. And after we receive the light, our body reacts to the light in some way to adjust ourselves. So the way our body regulates our blood flow is by changing the diameter of the blood vessels. There are, our blood vessel there's some smooth muscle. The smooth muscle can be relaxed, the sphincter, so there's going to be a bigger diameter, there's more blood flow. So that's how it works. In the case of chick embryo, it's very interesting. On the very early stage of chick embryo, the vascular wall hasn't been well developed. There's no functional smooth muscle to regulate with. And second, the nerve system of the chick embryo hasn't been well developed either. So this is one of the biological simple model that we want to use to regulate all the other possible factors. For example, it's known that UV light may enhance the blood flow. By UV light, it can relax the smooth muscle by asking the smooth muscle to secrete more nitric oxide. Yeah, so this is one of the known mechanism. Now, if we shine UV to the, oh, this is just an example. Now, if we shine UV to the embryo and blood flows faster, we know that because there's no vascular wall, there's no smooth muscle, and why the blood flow go faster. So that's going to be our question. Yeah, that's a very important part of my work, is to eliminate possible other explanations. And another good thing about chicken embryo is that it's small. It's like the size of a quarter. It's very small, and also it's flat. It's sitting on the yolk, and in an egg, it's just flat on the surface. So gravitation, we can consider gravitation as little as possible. So that's a good thing for me to. So the task was to look for a model that is as simple as possible, and chicken embryo, that's one of the simplest one. The idea of post-mortem blood circulation it's not a fresh idea. It's been known for a long time. Actually, it's been known for thousands of years. You know the word artery. Artery, the bigger vessel connects to the heart, which pumps the blood flow. The artery itself, it's from ancient Greek. It means air. That's because when the ancient Greeks they open up a dead body, they always found that vessel is empty. So they at the very beginning they think that artery is the conduct of air. So that's how they named it after. It's been observed for thousands of years that after people die, the artery is always empty. So where is the blood from? Where is the blood going? They must go somewhere. And also the post-mortem blood circulation has been observed, in mice, and also another group in chicken embryo. They had reported that. Actually, I learned this technique of how to euthanize chicken embryo from them. The biggest finding of mine is that, okay, so first, light. I was using infrared radiation can enhance the blood circulation. That's what I'm supposed to do. But what I excited most about is the direction of the blood flow in the post-mortem blood circulation. In the post-mortem blood circulation, after the heart stops beating, the blood flow is always following the original direction of the blood flow. It's from the heart to the artery and back to the capillary and to the vein and back to the heart. It's the same direction as if the heart is still beating, which means it's just like the blood vessel is driving the blood flow in a certain direction, in the right direction. So this is a very good news for me to find that the direction of the post-mortem blood circulation is in the same direction as if it's living. This can help me rule out lots of potential explanations. For example, I was shining IR to the chicken embryo. It's possible that it's the thermal gradient is causing the blood flow moving. And also I was using potassium chloride to euthanize the chicken embryo. So I introduced lots of chemical gradient into the heart. It's possible that the chemical gradient is inducing the post-mortem blood circulation. And also maybe because the embryo has been exposed in the air for a long time, so the constrict of the vessel is causing the post-mortem blood circulation. But none of these explanations is able to explain the fact that the blood circulation is still following the same direction.